Imagine that you were reading a great book, but that someone had removed a random series of pages. Without those missing pages, you might not be able to figure out relationships between characters and other plot details.
Geologists try to decipher the record of Earth's history as told in the rocks, but often there are parts of the story that are missing, rock layers that have been removed by erosion or never formed in the first place. In this lesson, we will use Plato and lots of photos from the Western U.S. to illustrate how geologists recognize those gaps in time.
Our learning objectives are that you'll be able to identify the characteristics of different types of features called unconformities, and to explain how they formed. These unconformities are the physical representation of a gap in time.
So what exactly is an unconformity? An unconformity is an erosion surface representing a gap in time between the formation of two sections of rock. If rocks have been eroded away or were not formed in the first place, we have no way of interpreting what was going on at that time in Earth's past.
Most unconformities are old erosion surfaces. We recognize them because the rocks above and below the surface have different orientations or different properties. There are three types of unconformities we would like you to learn about. Let's take a closer look at how these things form.
We will start with angular unconformities. First, imagine a series of horizontal layers of sedimentary rock forming under marine conditions. Next, we are going to uplift these rocks to the surface, similar to what might happen at a convergent plate boundary.
During uplift, the rock layers may be tilted, faulted, or folded so that are no longer in their horizontal configuration. Now that these rocks are exposed at the surface, the uppermost layers would be removed by erosion.
If these rocks are now resubmerged, new horizontal layers will be deposited on top of the erosion surface. The rocks above and below the unconformity have different orientations, and this surface between the folded lower layers and the horizontal upper layers represents an angular unconformity.
In this example from Utah, the angular unconformity places a tan-colored layer of sedimentary rock on top of tilted red-colored rocks.
Let's consider another situation where layers of sedimentary rock form under marine conditions. However, instead of tilting the layers, we are simply going to uplift them, erode some of the uppermost layers, and then resubmerge them.
Here's our original sequence of rocks. Now, here comes the erosion, removing some of those layers. Now we get renewed deposition, forming new horizontal layers that will be parallel to those that formed earlier.
So it can be difficult to tell where the unconformity surface is present. This type of unconformity is known as a disconformity. Geologists might look for evidence of old soil horizons between layers, or they might recognize that the fossils in the rocks above and below the erosion surface lived many millions of years apart.
In this example from Hungary, the different colored layers lie parallel to each other on either side of a disconformity.
The final type of unconformity is a nonconformity. A nonconformity places a sedimentary rock on top of igneous or metamorphic rock. These rocks may have been uplifted to the surface and exposed by erosion in mountain ranges that were subsequently slowly eroded before the region was resubmerged below a rising ocean.
Sedimentary rocks would be deposited above these igneous or metamorphic rocks that originally formed deep within Earth's crust.
In this example, a nonconformity places a sandstone formation on top of much older igneous rocks.
So let's practice your powers of interpretation. How would you classify the unconformities pictured here? In the left image, you can see that the sedimentary layers have different orientations above and below the unconformity surface. The surface itself is tilted, making the interpretation a little more challenging, but it parallels the layers above the unconformity. The layers to the right are more steeply inclined. Consequently, we would interpret this as an angular unconformity.
The other photograph shows a pair of disconformities in the Grand Canyon. The red wall limestone rests unconformably on top of both the Temple Butte Formation and the Muav limestone. Much of the Temple Butte Formation has been removed by erosion. The disconformity between the red wall and Muav formations represents a gap of over 160 million years.
Now, let's examine another image from the Grand Canyon. Turns out there are two well-defined unconformities in this view. The first is a nonconformity near the base of the section, and the second is a disconformity within the sedimentary rocks of the distant cliffs. Let's go find them.
We can actually see all three types of unconformities we discussed displayed in this figure. In the base of the canyon, we have igneous and metamorphic rocks that are overlain by the Tepete sandstone. This would be an example of a nonconformity.
This is what that looks like if you were to hike down to the bottom of the canyon. The surface is known as the Great Unconformity because it separates fossil-bearing sedimentary rocks and much older rock units formed before fossils became abundant.
Nearby, we have the rocks of the Grand Canyon supergroup that are overlain by the same sandstone layer. This is an example of an angular unconformity.
We can see the tilted layers of the older rocks below the light-colored, near-horizontal Tepete sandstone near the top of the image.
Finally, there are several places in this section where there are disconformities representing significant chunks of geologic time. Two of the most significant are represented by the red arrows. For example, as we mentioned earlier, the surface between the Red Wall and Muav limestones is approximately 160 million years.
However, when we look at these rocks in the walls of the canyon, it's nearly impossible to identify any significant differences that would tell us such a huge time gap was present between the units. It's only through careful examination of the fossils in the limestones that we can recognize the contrast.
So we have three different types of unconformities here, all one on top of each other, each representing a big chunk of time. So when we go to the Grand Canyon and we look at all those rocks, there's an impression that it must represent a vast array of geologic time. And it does, but it also represents huge gaps in geologic time.
You had two learning objectives for this lesson. How confident are you that you can accomplish both these tasks?